Okay. I think my employee ID ends in an even number, I hope. So I'm okay to be here. Okay, so Computer Science Mentors is an organization. Who knows about computer science? CSM? Yeah, it's really good. They really try to help. This is one of the things that people your generation do, as you guys help each other. I don't remember really doing that when I was your age, but that's great. It's wonderful, and you can go and help the people who are coming after you. Okay, so and the application is here. I think you press on this button, but I can't reach it, and it wouldn't work anyway. But okay, so you have to pay attention because the concepts in this class are very difficult to follow, and my jokes are even more difficult to follow. Okay, so you got to be sharp. Okay, so what are we doing? Okay. Okay, we have a web page. You could probably Google and find it, but it's here. All the slides will be posted on the web page. Okay, so we're going to mostly use Piazza. There's homeworks. There's lots of advice about homeworks on the web page, on the policy. The rules are straightforward. There's advice here. A lot of people want advice, and I think the advice is very good. The TAs, the staff have worked on the advice and looked it over, and we believe it's actually very useful for you. So go look at the course policies, and in addition, there's advice there on how to approach the course. Okay, this is me. I do this stuff. Algorithms, graph algorithms, optimization, approximation. Approximation means I sort of get things kind of correct. So, keep me on. If you have a confusion, just let me know. That was, again, one of my jokes. Okay, okay, I got a PhD. I have one, as hard as it may be to believe at certain points in time, but I do have one. And then I worked at a research lab for 10 years where I sat around and got to do whatever I want, and nobody really bothered me. It was pretty good. Then I worked at Akamai, and now I'm at Berkeley where I teach and have to raise grants. I'm not sure why I'm here, but actually, I love being here. It's a privilege. I have 3 kids who are roughly our age, so I know some of what you've gone through, and my kids, they have one Asian parent, so I also know that. So, yeah. Okay, Professor Alessandro Chiesa is going to come soon. You can Google him. He's very amazing, right? And so, that was a bit of a Trumpism. I apologize. But he is actually amazing. So, okay. So, does a list have a cycle? Let's start to do a little puzzle. So what does that mean? You want to check if a list has a cycle. And what you have access, you have access to a pointer to the first element, okay? Or a cell, right? Remember 61A or 61B? What do you do when you're at a cell? Well, you go to the next one. So that's essentially all you can do in this world. You could just look at the cell, maybe you could remember something about the cell, and that's it. Okay, and move on. Okay, that's it. Okay? So now, given this sort of access to the list, right? What can you figure out whether it has a cycle? So I'm going to give you an algorithm to do that. Okay, you mark the first node. You remember it, you put a mark on it, whatever, you use a hash table. There's different ways to mark things, but you mark the place where you start in the list. And then what can you do with the list? All you can do is look at the next one, right? That's the only thing you can do when you're in the middle of a list. Okay, so let's look at the next one. Let's see if that's the marked node, what must we know? We must have gone there before. In some sense, we must have seen it before. So that tells us if we see that the next cell is marked intuitively, if we keep, and then we go to the next cell. We're going to keep doing that. If there's a cycle, we expect to come back and see a marked cell. Right? If we see a marked cell, there's a cycle. Otherwise, you sort of go off the end of the list at some point. Right? If there's no cycle, you'll go off the end of the list. Okay. Either there's no next cell or it detects a cycle at some point. That's the claim. right? So what do you think? Who thinks it works? You know, it's a loaded answer, but who thinks it works if you didn't know I was trying to trick you? Okay, so now who's brave enough to have thought it worked? Okay, nobody's going to raise their hand. So let's just not go there. Okay, you got two options, yes or no. So we could vote. Who thinks it works? Okay, yeah, all right. Okay, no, but why not, right? I mean, in some sense, as a math guy, what I could do is say, look, voila, see, it doesn't work, right? You start at the first one, you mark it, and then you go around, okay? And then you never see the marked node. You go forever. You have you have no idea. It's like homework. You have no idea how long this is going to take. It just keeps going on and on and on, right? But that's not actually, the first node's not in the cycle. The answer is no. But this is like a math person's point of view. You know, they just tell you, okay, see how stupid you are, or see how stupid, I guess I'm the only one who answered yes, so me, right? But that's not how, you know, we as computer scientists have to be. We can actually think about, well, even the math people aren't like this. I'm making fun of them. I shouldn't because they're smart. But maybe let's try to prove this claim. Oh, no. Okay, so I added this at the end. Okay, so if this, is that, let me see if it's a display issue. Okay, let's try to prove the claim. Okay, so what is the intuition? I mean, it was a perfectly fine idea, right? If you're on a cycle, you eventually come back to the place where you start, right? That's the idea. And so now what happens is, that's the whole thing, and it's right. That intuition is correct. If you started at a point, and you mark that node, and you come back to it, you'll come back to it if you start on the cycle. Now, if you think about it hard, like how do I do that? Well, how do I actually formalize that? Well, right away I said, if you start on the cycle. Okay? And then I was like, well, what if you don't start on the cycle? And then I wrote the example. Right? So even the generation of the example is a process. It's not just check it and see, right? It embodies exactly the problem with our intuition. The first node is on the cycle. Okay? Does that make sense? Okay, so even when you're solving these puzzles, if you're getting a yes and no answer, constructing the counterexample is good, but it comes from a process. It comes from the process of, oh, okay, how does this work? First, there's an algorithm. Let's look at it. What is the intuition for the algorithm? Where does that fail? Can we tie it up and make it all clean? Does that make sense? Okay. Okay, so let's do it a different way. Let's do it a way that works. So let's have 2 pointers. The step is to advance pointer 1 twice. We're going to start with 2 pointers at cells at the first cell. Okay? And then we're going to advance one of the pointers twice and advance the other one once. And keep doing this until they meet again. And see if they meet again. Okay? Advance the pointer 2 once. If ever at the same place, you say, okay, there's a cycle. Because they had to come back to the same place, right? If there's no cycle, the one going twice as fast would just always be ahead, right? If there is a cycle, you know, if they all go back to the same place, that must mean there's a cycle. If there's no, right? If there's no cycle, they would never meet. If they do meet, there must be a cycle, right? It's just the contrapositive. Okay, so let's see it in action. So at some point, the blue pointer is here. Let's see how we argue it's correct. And at some point, the red pointer is here. And what we're going to do is, if no cycle, the slow pointer never catches the fast one. That's part of our argument. Okay? If there is a cycle, both pointers will enter the cycle at some time. At some point, it'll enter the cycle, right? If you're in a list and there's a cycle, you'll get into it, right? Okay, so now when you enter, there's some distance apart, where the blue one, you just chase the cycle until you get to the red one. You see how many hops there is, and you call that number D. Okay, that's the distance between the blue and the red. Okay, you go from the fast one to the red one, If it's a cycle, if they're on the same cycle, you know eventually from the blue one, you get to the red one, so this number D is well defined. Okay? Okay, now let's look at one step. So what happens here is the blue one, the blue one advances twice, right? It goes up twice. The red one advances once. So therefore, the distance between them decreases by 1. Okay? And then eventually the distance between them goes to 0. Okay? So you could talk about the runtime. If there's n steps to the cycle, there's n steps to catch up. So once you get in the cycle, it's at whatever the length of the cycle is, that's the maximum time for this algorithm to finish. Okay, so it's order n in terms of the size of the graph. So what other complexity can we talk about? Like we had talked, this has a lot of moving parts. First, we had to define the problem. We had to define what you can do in this context. Just go to the next cell. That was all we were really allowed to do. And also other things we might want to measure is how much space we used. And here we're just using 2 pointers. Okay. Even this one's a little bit iffy. This is a bit wrong. In what sense? I'm sort of assuming there's a first element here, right? Does that make sense? I'm assuming that I eventually get in the cycle. If I start at the end of the list, I don't know whether it's a cycle or not. Right? It could be that there's something hanging off the cycle, and I started my process there. So we're sort of assuming we're at the, quote, first element of the list, which already is a little fuzzy if the list is a cycle, because there's no first element. Okay? So you have to, even this one, you have to be a little careful with some of the details. But I think even the first algorithm is interesting, because it's capturing the intuition. It's like, okay, you start with a cycle, and you think about what happens on there. It fails, but then you see why it fails, and then you try to figure out something else that is using the same property. Okay, so puzzles, the solutions of the puzzles are algorithms which are correct, and in this class, we're going to try to make them efficient. Now, the question is this a useful process in general? I guess nobody really should need to be convinced at this point that algorithms are out there in the world, but here's one. What is that? What is that string? DNA? Yeah, DNA. So the way DNA is currently reconstructed is there's this, for example, the company Illumina. What it does is it dumps a big piece of DNA in, and it cuts it up into really pretty small pieces. And then it reassembles that all back together into a big piece of DNA, right? So you get little bitty pieces like this. They say, oh, I have a bunch of these around, the AGTAG, a bunch of these, and now I want to put these together to reconstruct this string. So you can, in this case, this is how you put them together. So this in the end gives you the string that I saw. Each one of these are little snips of non-overlapping pieces or overlapping pieces of this DNA. So this reconstruction is what's being done by Illumina. The computational method is enabling the technology, right? Before, the Human Genome Project used to use huge pieces, long sequences. And that was chemically, that was very, very difficult to do. So the computational innovation of putting this string back together just massively made this thing easier, where now you can go and do Ancestry.com and all this stuff, and it costs nothing, right? Okay, what is good on the web? Way back in the dark ages, probably almost before you were born, this web came into being, and it was a mess. We didn't know what to do with it, right? We didn't know how to find things on it. There's this thing called Yahoo. You probably don't know about Yahoo, but it was quite popular. What it would be was a big index of a big directory of everything on the internet. Okay, so but in the end, the search engines came along and said, okay, let's index it all and see what's going on out there. And now you've probably used these search engines before, and so you find things. At first, GoTo.com was the first search, was one of the early ones. And it was a mess, because they didn't know which ones people wanted. They couldn't tell which websites were the high quality ones and which ones were the low quality ones. How do you tell when the web starts? Which ones are good? Right? So these Sergey Brin and Larry Page, who are the founders of Google, they sort of posited, it was posited, and they came up with this sort of notion, is that, I guess it was a Google secret, so what they thought is look at people on the web. What do? They look at a web page, and then they click on something, and then they go to another web page. And then they click on something, and they go to another web page. Okay? So they viewed the ones that, if you followed this model, if people were randomly behaving this way, if they clicked on random web pages, the ones that they got to really often would be the popular pages. And back then, it wasn't so unreasonable, because what people would do is say, my favorite web page, right? And then they would list, oh, my favorite links. And so people were actually curating this idea. They were saying, hey, here are the links I like. Go see this, go see that. And it was really very, everybody's web page says, oh, this is what I enjoy. So it was a reasonable way that people were acting in those days. So PageRank is essentially a way to compute this process, the fixed point of this process. And it would tell you which one were their popular pages, and it worked really well. And it sort of distinguished, some people believe that it distinguished Google's quality from everybody else's. There was many websites, many search engines, and Google consistently gave people better answers. So this is an answer. It made us, as people who use the internet there, happy. It made Google a lot of money. Now, as soon as you have an algorithm, the world reacts. So back then, even right away, pretty much, once people understood this was the algorithm, people started making pages lots and lots of web pages that all pointed to each other. So then they would collect up all the random surfers, and they would be stuck in there, in this model. So algorithms is constantly evolving. Okay, so you have to find a new model for users. Right now, everybody searches, right? So already it's very different in the world you live in. Than the world I lived in. Okay, so Google, because now to find the good sites, you Google first, and then so it's sort of circular. All right. Okay, there's lots of examples: driving directions, airline scheduling, compiling, compression, cryptography, optimization. I worked at Akamai for a while. We were trying to find ways to deliver web pages fast. So we had caches. They have caches. They continued to exist even without me, as much as I feel that's great for them. And they continue to do this. They have caches all over the internet and serve you a lot of the content you do every day. And they use a lot of these ideas, actually optimization, load balancing, and so on. Okay, so now how do you want to do well in this class, right? So how do you do well? This is something I would hope most people already know, but maybe you don't. So this is a study in the 80s in the education literature. And it was a few randomized controlled studies where they took students and they put them in two conditions, and they measured the effect of these two treatments. Okay, the treatments are, do you give them, one group they gave one-on-one instruction and mastery learning, the other group they just did the regular classroom thing. These are 8th, 9th, 10th graders, math. So what they noticed is that the people who had this one-on-one instruction and mastery learning, they went from the 50th percentile to the 98th percentile, right? That's ridiculous. That means like the median Harvard applicant would get in, right? It's a crazy improvement, so crazy it's hard to believe. But it was done in the 80s, and so far the education literature hasn't falsified it. So it seems, and they have reconfirmed some of these effects. Okay, so this is an amazing thing. What does it tell you? Well, we don't really have one-on-one instructions. That was supposed to be a joke for 900 students. That's kind of hard. But we have a lot of resources, office hours. We pretty much have office hours all day, every day. We have piazza and discussion. And really, to me, it's about you. It says, really, people can do a lot better than they thought, right? There's a sort of fixed in growth, I guess is what they call it now, but there's a fixed view of intelligence. It seems garbage when you see that you can change people's performance at this level. And the one-on-one tutoring was really just a couple hours a week. So it didn't take that much, okay? And the theory around it, well, you know, I've read it some more, is that really it's maybe just sitting with the person, them making you do your work. It's not even clear that they were providing that much instruction. It's like the social pressure to not be on Facebook, right? I mean, there's really some, or to focus in the moment, right? It's really a tremendous thing. Focusing in the moment is what this class is about. I think it's what 70 was about. And so if you could find a way to do that, that'll be good. Okay, it's not long. It's easy to read in a sense, but it's mysterious. You really have to think about each sentence in some way. This is what I mean. You need that level of focus where somebody's watching you. Did you really understand that sentence? Can you explain that sentence to me? Okay. Okay, you work through the examples. You know, you got to take care to understand the arguments, right? Like that cycle argument is a little bit trivial, but you saw how I played with it. That playing with it needs to happen, right? Okay. Okay, you should do them. You know, there's rules about how you do them, and really follow this one, because otherwise you'll be sad on exams, really sad on exams. And they're fun. Yeah, they're fun. Okay, so now a quiz. So if the 50th, according to the Bloom effect, okay, blah, 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 what are you going to do? Perform at the 50th? The student may expect to perform at the 50th percentile, get into Harvard, be annoyed, perform at the 98th percentile, just to pay attention. Yeah, well, what I implied by my statement is 98th percentile. It's even unbelievable to me when I say it out loud, but those are what the studies seem to show. Okay. Okay, you know, as I said, when I read these studies are far from perfect, you know, and I phrase this with expect, as in expectation, and so that doesn't mean it works for every student, blah, 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 right? Okay, but still, focus and work seems to make a big difference. Okay, let's go back a little bit to 300 BC. Okay, so this is how they calculated back then. Okay, so that was 1. That's a good start. That's 5. They had symbols for each one of these. 1 is 10. I guess that's 100, 500. And 1,000, okay? So we'll just use those for now. And so now how do you write 8 with these symbols? You write a 5 and 1, 1, 1, and that's 8, right? 5 plus 3. I'm not sure what that is. I guess that's D is 500, C is 100, L is not on the list, but it's 50. Yeah, okay, well, I guess my mistakes are funnier than my jokes, apparently. Okay. Okay, so you will be very amused in that case. Sorry. Okay, so DCL, what's X? XX, okay, 10 plus 10. Okay, so whatever that is, you can add it up, I guess. I don't know. Okay, so, but this is what they did, right? This sucks, right? This is terrible, right? But we can try to work with it. Let's add them. Fine, we can do that. I can code up a number. It's not fun, but I can do it. But now, who wants to add them? Anybody want to add them in this form? Not looking at that? No, right? I assume nobody wants to. Well, okay, maybe somebody. Okay, fine. But now we have this. We do this way. We write this way. I guess this is 1448, and 670 is the first one. Oh, look, that's today. Okay. 670 years since the printing press, right? That's the other big invention, right? Of humankind. Okay? Okay, so now let's talk about multiplying Roman numbers. Who wants to multiply these? I mean, I don't like multiplying regular numbers, but this is ridiculous, right? Okay, so from India, this Al-Khwarizmi, I'm butchering the name, I'm sure. He brought this system from India, and he described all kinds of things. How do you add? How do you multiply? Solving quadratics. How do you solve quadratics? You complete the square, right? He invented that. That's what he did, right? So that's one of the things he did, and various other things. These are all algorithms, methods to solve problems by. Okay, and other people had these. It wasn't only many peoples invented these things. It wasn't only in India. It wasn't only this person who brought it back. But these things are people strive, right? And so this is 13 in the Mayans. They have base 20. I guess they wear sandals. The Babylonians had base 60. I don't know why. The abacus is some mysterious thing I don't really understand. My mom always claimed that, India, we invented zero. And I was like, well, that doesn't seem very good. But what she meant, I think, is the symbol, zero, because it's a placeholder for that position, as a placeholder for that position. And decimal symbols. All our symbols apparently are from India. I'm from Texas, but okay. So, in the 20th century, we use base 2, right? That's what computers use. That's what we're using underlying our computing systems, right? That's the input representation for modern computers. Computers could have done something else. For communication, it's very nice to have 2 levels. Okay. So, okay. So Al-Khwarizmi brought it partway back from India to Persia, and he's the Al-Khwarizmi may sound at least familiar because the word algorithm came from his name. That's a supposed picture of him. Nobody knows whether it's really a picture of him. It's clearly not a picture because they didn't have him, but Fibonacci is the one who brought it to the rest of the West. Okay? And this is a big deal, right? It's really like reading and arithmetic, right? Once you're there, it just accelerates everything. Okay? So let's think about Fibonacci a little bit. We have this, he also defined this, which is, I guess, a model for rabbits. In the nth day, the number of rabbits would be the number of rabbits on the n-1 day plus the number of rabbits on the n-2th day. Okay? So if you're small, everybody, you probably already wrote this in 61A or something. It's pretty trivial. You can write this recursive formula as a recursive procedure. And now in this class, we're going to talk about how to analyze it. And we're going to think about what this procedure means in a little bit more detail than you've already seen. Okay, is it correct? It's correct because it just implements the definition, right? Clearly, f of n is equal to f of n minus 1 plus f of n minus 2. That's just what you return when you pass in n. And you can check the base cases. Okay, so now the runtime, we're going to do this in this soft way. You've probably seen it in 61A and 61B. What's the general runtime here? We're going to say that it's a time we make a recursive call with parameter n minus 1 and a recursive call with parameter n minus 2. So the runtime is going to be whatever the time is for this call plus the time for this call plus whatever time you spent in that procedure, which we're just saying is two instructions. Okay, and then there's a base case. So notice that T of n actually has a kind of a close relationship with f of n, f sub n, right? It's basically T of n is going to be roughly at least as big as f of n. So the number of steps you take is really going to be about the same, or at least bigger than the number you output. Okay. Okay, so. Okay, you can, so now let's analyze it a little bit. F of n, let's just see how long it takes. And now I'm going to show you that this is a bad algorithm in a sense, right? It takes a very long time. You've done this, right? You've done it and you've seen it in practice that it takes a very long time. And so the way you can see that is you say that, well, f of n is equal to f of n minus 1 plus f of n minus 2. I unfold the recurrence one more time and replace the f of n minus 1 with f of n minus 2 plus f of n minus 3. And then I notice that I have two f of n minus 2s. So I know that f of n is bigger than 2 times f of n minus 2. OK? So by induction, that tells you that f of n is bigger than 2 to the n over 2, which means it grows very fast. OK? So from the book, this is how big f of n is. You can analyze it better, and you get some number like this, which means in some sense it's exponential. As n gets larger, this value, this number gets very big. OK? And so that tells you the running time is very big. So, so this says even if you have n equals 100, this takes forever, right? It just takes 2 to the some big number time. So this procedure was nice. It illustrated recursion. It's a disaster in terms of running time. So that's what we call a disaster, right? An exponential time algorithm, it's not efficient. We don't believe that's efficient. It's a bad algorithm, OK? You know, just the time grows very fast. I'm not saying, you know, it's somebody who wrote bad code. I'm saying the code is implementing a bad algorithm. Okay? It's not like you can change the code and to save a few instructions here. It's like as the problem size grows, the running time grows very fast. Okay, that's what we mean by bad algorithm. Okay, even if it's correct. So can you do better? So you've also probably done this. Everybody remember the iterative Fibonacci? Who did iterative Fibonacci? Yeah, so we can do that. So we can do this. We just count up to n, and we just sort of implement the recursion by adding the two previous elements of this list. It's a little slow to do it with the list, but that's how I wrote this code. Anyway. OK, so this is the main problem here. Like here you analyze this algorithm, the way you did it again in 61B, is you say, well, how many times do I go through this loop? And this loop only takes 1 time unit. I mean, if at least append is implemented quickly, well. If you have a good implementation of append, this takes constant time per iteration of this loop. OK. Yeah. OK, so I guess we can try it. So it should take order n time, I guess. OK. Let's see if I can do this. Should mirror the screen. Let me see if I can mirror the screen. OK, well, I could type this way. OK. Oh, no. I tried to make it a little better. It apparently went backwards. OK, let me move it over here so I can just see what I'm doing. OK. OK, now you can see what I'm doing. Ah, yes, maybe. OK, so there's a, OK, at 1 it's fine, at 1 it's fine, at 20 it's fine, at 21 it's OK. It's going up kind of fast. From 21 to 22, it almost doubled in time. OK, at 40, I don't know, what is it doing? Let me, while it's waiting, let's see if we can see what it's doing. OK, yeah, it's doing that. And these other things are just printing the timing. OK? And there's the iterative version, which is a slightly more efficient version of the iterative version. Oh, come on. OK, good. OK, so that was, it took 34 seconds, right? You can see that it's really growing fast. On the other hand, the inductive Fibonacci goes very fast. You could also notice a couple of other things. Let's look at the inductive Fibonacci here. Can you guys all see this? OK, so what I'm doing is printing the time it takes. So this iterative Fibonacci took 3 seconds here, and 9 seconds, and 3 seconds. Why is it doing that? It should be going, I'm going to claim this is a factor of 4 every time. OK? So roughly it's a factor of 4. Okay, I think maybe, I'm not sure exactly why it's not a factor of 4, but it should be about a factor of 4. Okay? So when you notice the argument, 12,800 is going up by a factor of 2, and the running time is going up by a factor of 4. Okay? So that's something to notice. Well, yeah, I don't know why it's 3. Okay, yeah, I know it's, it should be a factor of 4. I'm a little confused. No, it was a factor of 4 at home. Okay, but then it didn't crash, so that's different. Okay, let's see. Okay, but it's fine. Okay, let's say it's a factor. It's some factor. It's a constant factor every time. Let's see. Okay. Okay, this is why we should leave these things to John De Niro. Okay, but okay, let's go back to the. Okay. Okay, so now we have to think a little more carefully about the thing. It didn't. If it was going up linearly, I said it was order n time. If I double the size, the running time should have doubled. So it's faster than double, right? It went up more than double, at least. We all believe that. Every time I doubled the size, it went up by something more. I think there's a fixed constant there that's messed up. Okay, so, but let's say, just trust me that it's 4 for a minute. Sorry. And then say, okay, now what's going on here? Like in the inner loop, it was not really constant. What we were doing, we were adding 2 numbers. And the size of these numbers were growing in size rapidly, right? Like how big were they? We said they were 2 to the 0.64 n, roughly. And now, in terms of size, now after Al-Khwarizmi, what's the actual number of digits we need to represent that number? Right? We can't represent it in just one word of the computer. As you grow the number of digits, it's going to take a lot of space, and you're going to have to look at all those digits, right? And then you're adding those digits, which takes some more space. So now how long is each one of the numbers? How many bits are in f of n? Like when you're running the code, you really have to represent the whole number. So how many bits are in f sub n? Well, the value is 2 to the 0.694 times n. And the number of bits is log base 2 of n, right? The number of bits to represent that number is logarithmic in the size of the number, right? Okay, so it's roughly on the order of n. Okay, so how long does it take to compute f of n minus 1 plus f of n minus 2? O of n. So each step through the loop was O of n, roughly. Okay, so each time you go through the loop, you go through n times, and on average, the size of the numbers are around n over 2 or some constant times n, and therefore the total number of operations is O of n squared. Okay? So that's what's happening there. So even when you analyze the inductive thing, you have to be careful, and you have to think all the way back to pre-Arabic times where we're really worrying about the size of the representation as well. Okay? Okay, so you can't hide this addition. You can't hide this big complex operation and say that costs 1. It doesn't in this case. Okay, so doubling size made the fastfib grow by roughly a factor of 4. Okay, so now it should be 4, and this is why I think it's 4. Okay, so the idea is the runtime is sort of grows proportional to n squared. It's some constant times n squared. Okay? N is the size of the problem. N is the size of the problem here. So if we double n, what will this runtime be? Okay, we're going to change n to 2n. So we're going to replace n by 2n, and we get c times 2n quantity squared. Right? Which gives you 4 times c n squared. Okay? So it says when you double the size of the problem, you would expect the runtime to go up by a factor of 4. Okay? So that's what an n squared time algorithm does. And that's what this sort of rough asymptotic analysis does for you. It tells you if you scale the problem by a certain factor, it tells you what factor the runtime grows by, or your runtime bound. Okay? So in particular, for any polynomial time algorithm, it has this form, n to the k for some constant k. And you scale the input by some constant c, it grows by c to the k. So we were scaling the inputs in our example by a factor of 2. And since k in our example should have been 2, it should have grown by 2 squared, which is 4. Okay? So the doubling size scales the runtime by a constant for polynomial time algorithms. It's just not true for exponential time algorithms. So those it squares the runtime. It just makes it go much faster. I mean, much slower. Right? You saw Fibonacci of 20 took like no time. Fibonacci of 40 took forever. Okay? So it really gets it takes a lot more time as you grow. So this is the notion of efficiency that that we almost always talk about here, is what's polynomial time. Okay? And it also has this whole notion of what's the size of the input, right? For numbers, the size of the input is a number of bits to represent it. Okay, so asymptotic analysis says, okay. Sorry. So let me just review this. I think you've seen it before. We're going to do it a little bit more formally in the homeworks. Okay, so it says O of n means it's just roughly grows by n, by O of n. So you don't care about whether it's n minus 2 or n minus 10. So, this is like 61A or B. The style of your loops, it doesn't really matter. And one could even argue that maybe in 61C they care about the constants a little more, but we're going to show you an example that even in 61C, the asymptotic behavior can actually be much more important. Okay? So your recursive fib has a much simpler and faster loop, but the iterative fib just dominates once the size of the problem becomes reasonable. And this is the time for recursive fib. This is the time for iterative fib, and so on. Okay? So if you double n, it squares the runtime, and we saw that in our example. Again, if you go from 20 to 40, it's a disaster. The other program was running on 100,000, and it was fine. Okay? It should multiply the runtime by 4. Okay? So again, we're refreshing this. You should have seen it before. We're going to do it a little bit more formally in our first homework. And you've seen it a few times. You saw it in 61A and B, and you also saw it in high school a little bit, right? So let me show you. So 2n squared is asymptotically the same as 4n squared when you took the ratio of two things, of two functions with some polynomial on the top and the polynomial on the bottom. It would either converge or diverge, and that was really asymptotic analysis, right? Like if you take the ratio of these two expressions as n goes to infinity, it converges, okay? So both are O of n squared. 4 log n is asymptotically the same as 100 log n. Both are O of log n. If you take the ratios of these things and take n to infinity, it's going to converge to a constant, or something smaller than a constant. Okay, so you ignore smaller order terms, like 2n squared plus 100 is O of n squared. 2n squared plus 1,000 log n. Now this seems worse because you're not adding a constant, you're adding something that goes to infinity. Again, if you take the ratios of these things, of this over this, you get that it converges to a constant. Okay? And it's an upper bound. N squared is O of n cubed. Log n is O of n, because n goes to infinity faster than log n. So now what you're doing here is you take the ratio of n squared over n cubed. You take the limit as n goes to infinity. It should go to 0 or to a constant. Either one works for saying it's big O. Okay, so this is another way of saying it. It says if you take this ratio, f of n over g of n as n goes to infinity, you get something that actually converges. Okay, that's what mathematically it works out to. This is another statement. This is the way the book states it. But I think you've seen those ratios things in high school, at least in California. Okay? Okay, so there's more asymptotic notation, which is, okay. Let me go quick, and I'll give you a little break, and then we'll do something else. Okay? Okay. So omega is a lower bound. So it's exactly the same, almost the same as O, except 2 of n squared is omega of n squared, and omega of n. It means 2 of n squared grows faster, or at least as fast as n squared. So 2n squared grows at least as fast as n, as the function n. Okay? And then from here it sort of works out. It's just the other way. Okay? Okay, so now theta, when we say theta, what we mean is that this function is theta of that function if it's both grows, if essentially the ratio converges to a constant that's not 0. Okay? It says g of n is big O of is less than, grows no faster than f of n, and g of n grows at least as fast as f of n. Okay, that's what theta means. Okay? Okay, so let me give you a little break, and then we'll come back in like 5 minutes. Why? Yeah. And how many steps are there?
So I was thinking like because it's both, it's like both n and every step. It's not like theta of n. So like.
It's sort of theta then.
Really?
Yeah, but I just said, oh, you're right. That's why maybe it's not 4.
Yeah.
That's what you're trying to come up with a theory why it's not 4.
It'd be something like.
Right, but it is 4. It is n squared. It's theta of n squared.
Oh, really?
Because you sort of have to look at all the bits of the number, right? Because each number is n bits, and you're adding them. And
But each number is like you're starting from like 0 and going all the way up to.
yeah, but on average they're about n bits. The middle one is about half of n bits, right? The last one is 0.64 times n. The middle one is going to be 0.35 times n. So the last half of them will be all at least 0.35 times n. So it's n over 2 times 0.35 times n, and then you get an n squared and some constant in front. And we don't care about the constant, right? Yeah.
Hi, can I give like a really quick little blurb? HKN's hosting an info session tonight for Accenture Labs, which is like a company.
Yeah, no, we don't. I didn't. That's why I didn't do the CSM.
Okay.
Yeah. So.
Okay.
But yeah, sorry. Yeah. Hi.
Do you mind if I go out in the hallway and
No, sure. That's what you need to do. That's no big deal. All right. Okay. Okay. All right. Okay. All right. Woohoo! Woohoo! All right. Okay. So I'm gonna. Who now you should know. You should love arithmetic, right? So we're gonna do some arithmetic, but I'm gonna show you something amazing. Like it still shocks me, all right? Like remember multiplication? Okay. Well, with Roman numerals, it sucks. With even regular, I don't know whether you had to do this because you're different. You're post-internet, but we used to, did you have to multiply big long numbers together? Yeah, that wasn't fun, right? Okay, so we're going to show you that the one can do better than that. I mean, it seems a little shocking to me even still. So let's just go over what we knew in grade school, which is always fun, without the coloring, and then we'll show you this cool idea that you can do much better. Okay, so okay. So addition, okay, that's a big number. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 10-digit number. And this is another 10-digit number. You know how to add it. Yeah, how do you add it? You add the first digit, you carry, and so on. Okay? And the time is order n. Okay, if there's n bits or n digits in this, in your example, if you have two n-digit numbers, the time to add them together is order n. Okay, that's what we used in the fib example. Oh, by the way, here, I just didn't have it big enough. I guess the low order terms do matter for a while. So you do eventually get closer to a factor of 4. Okay, anyway. All I did is add a 0. I just made it bigger, right? That's the whole point of asymptotic analysis. It's also what people criticize us for because sometimes the low order terms throw you off a little bit. Okay, so I didn't change the code. Okay, so anyway, can we do better? We need to look at the numbers to add them. So in some sense, there's some argument here, at least there's a reasonable argument here that's sort of really grounded in fact that you can't do better than order n. If you have an input of size n, you probably want to look at the whole thing. Okay, so this is probably as well as you can do. Or in a sense, it must be as well as you can do. Okay? If you want to, because you have to output something that's of size n. So to write down the output is of size n. So in some sense, you can't do better than how much time it takes to write it down. Okay? So that's another, it's amazing that somebody invented this, right? Had to bring this over. Right? They didn't have this. So we know how to do this. We multiply this whole number by 1. We write it down. We multiply this whole number by 9. And we write it down, and so on. And now the number of digits here is the number of rows in this sort of tableau is n. There's n rows in this tableau. So the number of things we're writing down here is there's roughly n things in each row. Like, again, I'm ignoring constants, right? It could be n, it could be 2n. But something on the order of n. And so there's n rows, all of size around n. So the total time is O of n squared. It's also theta of n squared. Okay? Okay, so a multiplication takes O of n squared time, right? That's what we've shown. Is this the best possible? And I've already told you the answer again. But here's why you sort of believe it's the best possible. Is every digit in x in your number, let's think of two numbers, x and y. They're numbers. They're n-digit numbers or n-bit numbers. Doesn't matter. Every digit in x must multiply every digit in y. At some point they have to meet, right? You saw that in this example, the digit 6 here touches that one and that one and that one and that one and that one to make the 6th row. Okay? So it seems like that's pretty fundamental. Okay, and there's theta of n squared pairs, and it seems like you have to at least do that much work. Right? So is this the best possible? So that was supposed to lead you into saying yes, but the answer is no, you can do better. Okay? Okay. Okay. Yeah, that's what, really? No way. Right? How is this possible? I'm not even sure it's true. I'm just nervous about the rest of the lecture. Okay. Oh, really? Okay, let me show you. Okay, so we're going to do this thing. We're skipping the rest of chapter 1. We're going to go quickly to chapter 2. Okay. So here's multiplication. Now again, it's very important to get all these things straight in your head. X and Y. Okay, that's one. X is an n-digit number. Y is an n-digit number. Okay. And we're trying to multiply together, and we're going to try to get x times y. Okay? And just to remember intuition, if x is n digits and y is n digits, x times y is going to be 2 times n digits, roughly. Okay? When you square a number, it doubles the number of digits that you need. Okay? That's something else to get in your intuition. Okay? So this thing is roughly to scale. Okay? X times y, this number of, these are, in a computer, x has a meaning as a number, but we think of it as a sequence of digits. And y is a sequence of digits, and x times y is a sequence of digits, which is roughly twice as long. Okay? Okay, so now we can think of the kth place of xy as a coefficient of 2 to the k. So if we look at these digits and we look at the kth place in here, it's just the coefficient of 2 to the k. It's like 10's place, 100's place, and so on. It's like 2's place, 4's place, 8's place. Okay? So now if you want to get it, this digit tells you how many 2 to the k's you have here. And now you multiply that by y0, which is what you do when you multiply. And this tells you how many 2 to the k minus 1's are there. And then you multiply by the bit y1 times 2 to the 1. So when you multiply these two place values together, you get a 2 to the 1 and a 2 to the k minus 1. Which is a 2 to the k. It's the value at 2 to the k. Okay? So in some sense, it's sort of like this. I mean, there's some carries. Forget about the carries for now. But for now, we're gonna think of ak as computing these coefficients. The coefficient of 2 to the k. Okay? And again, the way you do it is you multiply xk times y0, xk minus 1 times y1, xk minus 2 times y2. The indices should add to k. And that's what we're doing here. I plus k minus I is equal to k. Okay? So in some sense, now that you know that that's the place value, then you can add them up. And here you may carry. This is where you deal with the carries. Because a sub k may not be 0 or 1. Right? It may be a big number, so you get some carries. When you add them all up, then you get back the number. So there's another way of multiplying. And what you see here is all the AKs are the all pairs multiplications. Right? You have all the pairs of multiplications that you thought you should have. Okay, so number of basic operations is basically theta of n squared, just like I argued before. And this is another way to view multiplication in terms of basic operations. Okay, so now you have two n-bit numbers again, and now I'm going to define a couple of more symbols you should know. These are the highest n over 2 bits, and these are the lowest n over 2 bits. And okay, and so the highest are XL, they're on the left. The lowest are XR. So what is XL? It's n over 2 bits. Represents a number. But XL over here is just the value of that number. That's what I'm using it as. We represent in the computer as a sequence of bits. But we're just talking, XL here is just the value of this number. So X is a value of this number. I can express it this way. It's 2 to the n over 2. You just shift over XL by n over 2 positions. And then you add in XR, the low order bits. Okay? And that's the same for Y. So now we have 4 things. XL, XR, YL, YR. Okay, so now we want to multiply them together. So let's look at this again. Okay? So x plus x times y, now that we define this thing, what we're doing is we're shooting for a recursive algorithm. Right? We're dividing the problem into half. We're taking each half of the numbers, right? And trying to figure out how to piece together a multiplication of the two big numbers with multiplications of the small ones. Okay, that's where we're going. Okay, so we can say, well, if I'm just now replacing x with its representation there, with those symbols, and the representation of y with those symbols, and I get this product here. And now that's a two-term product, so we could use FOIL, right? And we see that what we get here, this term is 2 to the n over 2 times xl times 2 to the n over 2 times yl. This last one is xr times yr, and then this is the cross terms. And the cross terms contain this 2 to the n over 2. Okay? Okay. Okay, so now if you think of it as a recursive algorithm, instead of thinking of this as a value of the number, think of it as an n over 2 bit representation. So you have to go a little bit back and forth here. So this is just a multiplication between two numbers that are n over 2 bits. So it's a recursive. You can make a recursive call to your procedure, your multiplication procedure. And this is 2. This is also a multiplication of two n over 2 bit numbers, and this is, and this is. Okay? So there's 4 products. Okay? And now you're reducing, what we're trying to do is reduce the computation of x times y into the computation of, which are both n-bit numbers, into the computation subproblems, where each of the problems is now a multiplication of smaller numbers. And they're way smaller. They're half as big. Okay? But we get 4 of them. Okay? Okay, so now we have a recurrence. We can now, making the subroutine call with the appropriate code, you can actually just write this out. It's really easy. Okay? And now you can write down the recurrence for how much time it takes. It takes the time for an n-bit number is you have to do 4 n over 2 bit number multiplications, and then you have to add them up again. You have to do this last bit where you shift over by n bits, you shift over by n over 2 bits, you add these two, you add them all together. And that's order n time. Okay, so this is the recurrence. Okay, so now we took our grade school algorithm and we changed it into a recursive algorithm. We figure out the runtime of that recursive algorithm. It's 4 times t of n over 2 plus O of n. Right? Okay, so have we done better? Is this faster? If you solve this recurrence, what do you think it's going to be? Is it going to be faster or is it going to be worse? Okay, well, think about the recursion tree if you're good at that, I guess. Okay, so it's a degree 4 tree of depth log 2n, and then something happens, and then that's the number of leaves. And the leaves are theta of n squared. And what do you think those n squared operations are? One digit multiplying another digit. It's exactly the same problem we had before. In the end, you're going to have a recursive call that says, oh, I'm multiplying this digit by that digit. And that's all you're doing. Just a different way to do the same basic operations. Okay, so it's nice, I guess, but it's 1 for each pair of digits. Okay, so again, we've gotten nowhere. I've got a fancy recursive algorithm that doesn't do anything in terms of getting better results. Yeah, I didn't really okay, so there's a, I knew the answer. That's how I did it, but we're going to have a formula to solve recurrences like this shortly. Okay, so do you want a demo? It's always a risk to do a demo. You guys want a demo? Okay, no, okay. Okay, one thing to notice is that the number of bits to represent 3 to the n and 3 to the 2n, there's twice as many bits in the representation of 3 to the 2n. Okay? That's just what, I mean, that's, okay, so let's see. Come on. Okay. Okay, so now I'm telling you what factor it went up by. So they went up by a factor of 4 at the beginning, right? If you go back. Here, when you double, so I'm multiplying 3 to the sum 10,000 by 7 to the 10,000, and you see that it's going up by roughly a factor of 4. There's some small order terms, but every time I double the size of the number, it's going up by a factor of 4. Okay, now I'm just doing a different one. Okay, that was a demo of that recursive algorithm, and now I'm going to test a new algorithm. Here's this new algorithm. I'm just multiplying the numbers, x times y. Okay, what does that mean when I say x times y? It means Python is doing it. Python has some algorithm to do it. Okay, so I'm just testing Python's algorithm. The first one was a test of code I wrote, the recursive code that I just described. The second one is just calling the Python algorithm. Okay, and now let's see which one's better. I mean, not by constant factors and how it scales. That's the important thing here. Okay, so now Python, oh, it's only growing by 3 every time. Right? As we double the size of the numbers, we're only growing the multiplication by 3. Right? It seems like you shouldn't be able to do better than n squared. This is somehow doing better than it. It's scaling less bad than a factor of 4 every time when you double the numbers. So it's way better. Okay? Okay, so yeah, really. Really, yeah, right? Really. I mean, we see it. Okay, so what we see is this, as n goes to 2n, the running time goes up by 4 in the elementary school multiplication code. If as n goes to 2n, the running time goes up by 3t. The next few lines that might frighten you, they frighten me. Don't worry about them. Blah, and then blah, and then blah. Oh, look, instead of going n squared, we get n to the log base 2 of 3, which is really n to the 1.58, which is much better, right? Because if you start doubling the numbers a few times, multiplying by 4 every time is much, much slower than multiplying by 3 every time. So it scales less. It scales significantly less. Less than n squared, meaning that all the digits aren't somehow multiplying each other, right? It's defying our argument about a lower bound. A little flaky. Okay, so much better than grade school. Okay, finally. Okay, so let's go back to something else. How do you multiply complex numbers? So you have this expression over here. You get 3 plus 2i, where I is the imaginary, is what? What is I? The square root of negative 1, right? It's the imaginary number. 2i is the imaginary number. And you multiply by 4 plus 5i. I'm doing FOIL here to multiply out the expression using I formally. Okay. And then I remember that I squared is negative 1. And so I can simplify. And I could do 12 minus 10 plus 7i. And I think that's 2 to plus. That's all fine, right? Okay, but that's great. No problem. Okay, who wants to do that? Okay, so I don't want to do that. Okay. And you know who else didn't want to do that? Gauss didn't want to do that. And Gauss didn't have computers. So he had to do that. Like he was multiplying complex numbers. The man was a mad person, right? So he said, well, okay, let's look at this. Okay, so this is the expression I derived before. Really, this product is AC minus BD. The minus BD comes from the I squared, which gives you the negative 1. Okay, and again, it has 4 multiplications, right? Does this look familiar? Looks like 4 multiplications we had in the recursive description of multiplication. Okay? Okay, so now, so there's 4 multiplications. That's and he would, every multiplication is a pain. Every multiplication is a pain for Gauss, right? Because he has to write it out. It's those big numbers, right? And so he's like, oh man, look, can I do it with fewer? So he said, well, let me do this. Let me do something like stupid. Okay, really stupid. Okay, let's just drop the i's. Okay, let's multiply these two together. A plus, I don't know how he figured it out. I don't know Gauss. A plus B times C plus D. So he noticed this, right? That if you multiply this out, you get like 4 terms. It's not really what you want. You want each one of these terms separately, right? But you get these 4 terms. And it's like, at least I get all the 4 terms added up. I guess that's something. Okay, but so you get like 4 products here. You get all the things you wanted, except they're sort of munged together, right? That's the technical term. Okay. So now let's see. Let's look at P2. I can also multiply AC and BD. And then I want this term, right? I'm looking for this term. Now I have AC. That's, it should be AC, right? And I have BD. And AC minus BD is equal to P2 minus P3. So now I can compute this term. Okay? Now I want to compute this term. Do you see how I can compute this term with P1, P2, and P3? Can I subtract? Yeah, subtraction. Awesome. Okay, so I could take P1 and I could subtract out AC and subtract out BD and then get AD plus BC. Right? So now I've only done 3 multiplications, P1, P2, and P3, and yet I can reconstruct the object I wanted. Okay? So he really literally had to do only 3 multiplications instead of 4. Okay? Okay. You have to do an extra addition or subtraction, a couple of subtractions. But who would rather do a subtraction than a multiplication? Like I would. Okay? It's a lot faster. It's O of n, right? So it's fine. So you're replacing that. You're still doing O of n work. It's all fine. Okay. Okay, so now this should all look kind of vaguely familiar, right? With XL, XR, YL, YR, right? There's 4 subroutines. We used FOIL, and we then called multiplication again. Okay, so let's do that. Okay, so now we have our 2 numbers. We have X and Y. We have that the product is this thing. So what do we need to do? We need to recursively, what we said before is we needed to compute XL-YL, XL-YR, XR-YL, and XR-YR. But that's not really what we needed to compute. What we needed to compute is this, and this sum, right? We didn't necessarily care what XL-YR is or XR-YL is. They're added together. Okay, so we only needed these 3 terms. Okay, so we use these 4 n over 2-bit multiplications to produce these 3 terms, right? Because we can get the middle term by adding up 2 of these other terms. So, in fact, can you compute these 3 terms with only 3 multiplications? Yeah. Yeah. I always give away my answers. Maybe I need to rethink how I lecture. But okay, so we need these 3 terms. So here's one term, the PL, XL plus XR, which is ridiculous. This is ridiculous, right? We're adding the high order bits and the low order bits. That's just ridiculous. Why are we doing that? Doesn't make any sense. But we're doing it. What the heck? And we get it, but we know that this product is a sum of all these things. It's algebra. It's the magic of algebra, right? That it works, like things with fields. Okay, so and P2 is XL times YL, P3 is XR times YR, and what we're trying to do, so that's P2 is exactly this term, P3 is exactly this term, and the middle term, this term is this term minus these 2 terms, right? Okay, so now what we've done is we've only used 3 multiplications. Okay? So we get this different running time bound. I mean, technically, it's a little bit different, right? Because what we're doing here, when we add these 2 numbers, they're 2 n over 2-bit numbers. And when you add 2 n over 2-bit numbers, you might get an n over 2 plus 1-bit number, but it's close enough. Okay? Okay. Okay, so now we have this recurrence. The runtime is what? Which one of those 2? Which one of those 3? Yay! C. Right? And again, I get this from unfolding the. Really, the proof I'm telling you is unfolding the recursion tree. You see, the degree of the tree is 3, and then you just calculate the depth, and then you raise the degree to the power of the depth. And that's what this is doing, okay? And you'll see it next time. Okay, so multiplication algorithm with this. And wait, still you should be a little confused. The exclamation points means I'm excited, because sometimes I'm deadpan, but I'm really excited, so I'm really excited. Really, really excited. So, but look, what happened? I kept telling you every digit has to touch every other digit. Where did that happen? It did happen. It kind of did happen. So you can think about that, okay? I mean, you shouldn't go away thinking that's all there is to it. You should be asking yourself questions.